Hey, stats class. Welcome back, kind of to your stats class here. I thought I would take time here since we're going to try and get back into things and discuss how the coronavirus thing relates to your statistics class. Specifically with you guys, I want to talk about what we here refer to as the flattening of the curve, and statistically, what does that kind of mean to us? I saw an article here back on the 17th from the Washington Post that they said why outbreaks like the coronavirus spread exponentially and how to flatten the curve. So I wanted to look first at the idea of it spreading exponentially. This is kind of an algebraic thing. But real quickly, what they mean by the flattening the curve, or what they're wanting to do with that. And it has to do with this right here. If you look at this picture over here on the side of the screen, they've got obviously a bunch of matches piled up here together that all burned up. And the idea would be there's two ways this thing's going to pan out here. We could have this situation where we get it done and over with real fast. You got all the matches stacked up close together. You light one and it'll just go right down the line, light them all, and it'll be done real quick. Or if you spread them out a little bit, they're still going to light and burn, but it's not going to happen as fast because it can't jump from the first one to, say, the second or the third until it gets one at a time. It kind of has to go one at a time. There'll be parts that'll be grouped up, but there'll be gaps in other places if they can be spread out. Social distancing, there's our term right there, social distancing. All the matches are still going to burn, just not as quickly. And that's the goal here when they talk about this flattening of the curve. And this would be the two scenarios here. This is, as it says, without protective measures. Basically, it's going to go real fast. That's one option. The problem with that option is our healthcare system can only handle so much. You get above what it can handle, and just like in some other countries, they're going to end up sending people home. And the mortality rate, how quickly people die, or the amount of people die, it's going to go up because they can't receive any treatment at all. If we can keep it within the parameters of what our hospitals and clinics can handle, it should help keep the mortality rate lower. Well, that's what this flattening the curve is about. The give and take to this deal is, though, just like with the matches, pretty much we know that 40% of the population is probably going to get the coronavirus. It's just how quickly they get it. So if we flatten out this curve, right, like this, it's the same amount as the big tall one, is just spread over a longer period of time, which means it'll take longer, that we'll have to deal with the other consequences, some of the economic consequences that a lot of us, myself included, are having to go through with some of this. But the goal with the why we don't have school right now, at least on campus, is to flatten this curve, and the whole point of that is to truly save lives. It's discouraging, it's frustrating that we're not together. Me, just as much as you guys. I miss you guys. I wish you were here. But I know that in the long run, we're all doing this to save probably somebody else's life, but to save lives so that we don't spread it, especially to the parts of our population that are really susceptible to this being deadly to them. I know that your age group, you're not in that age group, but you guys know what I'm talking about, the old and those that have underlying health issues. So I don't know if that helps or not, but we're saving lives by not coming to school. So I do want to go through this quick. Back to the comment that it's exponential. Why is it exponential? I know this is a little bit of algebra here, but that just has to do with the ratios between two numbers. If I say, 2 times 2 is 4, times another 2 is 8, times another 2 is 16, and so on and so forth. If I take any of those two consecutive numbers and divide the bigger by the smaller, I get 2 because I was multiplying by 2's. Anytime that's true, when you can take two consecutive numbers and get basically the same thing, you're talking about something that's exponential. So I did that. I went to the CDC website And here's the days since we started getting people in the United States. It's just US. With coronavirus, this is how many on each day. You can see it's the statistics right here. Some days it's more, some days it's less as far as how many are being added to the list. But I went through and I set up just ratios. Okay, so like 29 divided by 15 is 1.9. 35 divided by 29 is 1.2. Again, if it's exponential, then these ratios should approximately kind of stay the same, which they kind of do if you look at it. The first final was really high, 1.9. But then 1.2, 1.1, 1.3. You can see a lot of 1.3s, a lot of 1.4s, a couple 1.5s at the end down here. I averaged them out, add them all up, and divide by how many. The mean here was 1.2, which means essentially from day to day you're multiplying the amount by 1.2 to get to the next one on average. As my statistics class, you guys probably understand that a little better than some of my other classes. So I would say, yep, this thing's exponential. From that, I can do an equation. If you remember back to your algebra days, you've got, what did you start with? What are you going to end with? You've got here what you're multiplying by every time, 1.2 in this case, and how many times are you multiplying by that? And also how many days went by. Now, the Washington Post made a claim that it was doubling about every 3 days. So I just counted off every third day, and I did the same thing. I divided, and that's where these numbers are coming from. I went back over to here. I did 38 divided by 15, and then I did 54 divided by 38, and so on and so forth. That's where these numbers are coming from. And I averaged them out again, just added them up, divided. And the Washington Post is pretty close here, just over 2. So yeah, it's pretty much doubling at this point. About every 3 days. So yeah, you're going to see these numbers because it's exponential, sort of. You're going to see these numbers grow more and more. I wrote a different equation here that we could use for doubling. You just have to remember this is every 3 days. Is it exponential? Sort of. So all of you guys have had college pre-calc at this point, and we discussed exponential functions and the different kinds of exponential functions. I think you guys understand that this is going to fit the bell curve, the normal curve, which is what we call it in statistics, also called the Gaussian curve, but in stats we typically call it the normal curve. And this is the function that goes with it. And since you're my stats students, you should recognize some of these symbols. You've got your population average, your population standard deviation. This would be just a value. It should follow that. The question right now is, what is going to be the population mean? Sorry, I think I said that wrong a minute ago. What's population mean? What's it going to be? What's the population standard deviation? Especially the standard deviation, I don't know that we know what that's going to be. In fact, we're trying to change it. And I'll come back to that we're trying to change the standard deviation. So it's probably on the move. I took this though, and I thought, I've got a lot of students that have emailed me, stopped in and say hi, and they've asked, how long until you think we're going to get back? So I thought, I'll do a little analysis here, and I'll be the first to admit this is not going to be a good analysis. I'll explain more at the end why I know it's not. Some of it is my underlying assumptions. To do this, though, the question is, okay, well, if I can figure out how long it takes to get to the top, because if I'm following an exponential growth model kind of coming up like this, how long to get to the top, then I could just double it to how long to get back to the bottom till it's, ending. You've got to recognize right away that the exponential growth part is only the first portion right in through here. After that, when it starts to slow down, this is no longer exponential growth because this isn't a simple exponential growth. This is a normal curve, okay, the stuff that we've talked about in statistics. But I'm just, for approximation reasons, I'll just use the exponential one. Now, some numbers, some facts that you can look up, sort of. One of them is they're saying that this thing has an infection rate of 40%. So 40% of people are going to initially get this. The U.S. population right now is at 327 million. Take 40% of that, and you end up with 130,800,000 people. So, okay, I've got what 40% is. Okay, so should actually be my mean if I was to put that into my equation. To cut it in half, though, oh, excuse me, I did say that wrong. That would be the whole amount. 40% would be everybody. I'm going to cut it in half to get, well, where would halfway be? And I come up with 6,540,000. Now, I'm just going to use that that model I came up with, exponential growth, for every third day of doubling. And it would be this. What did I start out with? What am I ending with? 2.1. And the question is, how many times is it going to do that? And then I'll, of course, have to multiply by 3 because this is for every third day. So I'll divide by 15. And if you don't remember this stuff from pre-calc, it's okay. But I'll take the log of both sides here. I have to do what's called the change of base formula. Some of you might remember that term, change of base formula. And then I'm going to divide, and I end up with just about 21 days. That would be 21 times that it does this a little bit more than doubling. Well, it's not actually 21 days, though, because this was doubling every third day. So you triple that. 62, 63, however you want to round that. That would be to get to the middle. And then, of course, to get to the end, well, you'd have to double that. So you're looking at, I don't know, somewhere around 2 months to get to the middle and 4 months to get to the end. But like I said, this is not a great approximation because this isn't actually a good model, because the exponential curve part is only at the beginning. We are still here. I know we're still here because the rate of change is getting bigger still. What's going to happen is once I get to about here, the rate of change, that ratio between the days, is going to start to get a little bit smaller as I get to the top, and then eventually it turns negative. But it's still growing, so I know that we're still in this growth period right here. Because it's going to slow down, this model actually only works for the first portion. It would get me there a little faster than it actually would go. So where this puts us out at 2 months, I would say that's probably more like 3, maybe 3.5 months. Then you got to double that, 6, 7 months before we get to the end of it. When it stops affecting our lives as much, I don't know. The government has to make those calls. Other issues with this model is the fact that I assumed 40%. I don't know that they have that number down for sure. That's an estimate at this point. The second thing I hear, yeah, I already said it's not going to stay exponential, not at least with a basic equation the whole time. It'll follow that Gaussian curve, that normal distribution formula eventually. But then the third part is we're trying to flatten it, and it's not flat right now, and we're working at it. I would like to address that as my statistics students, though. In statistics, we've talked about variation and standard deviation. We'll be talking about it a lot more. But this is what we're trying to change, the standard deviation. We're trying to spread it out, make it a bigger standard deviation from the mean as we're trying to flatten the curve here. So that is a goal. Whether we can achieve it or not, I don't know. They say that we kind of are already, but this would be the goal. Like I said, I'm trying to do a trial run here. This is new to me too, videoing myself. It's strange for me to see my face on the screen, which I'm sure you guys are going to feel the same way. But I hope to see you at least on some face-to-face level, maybe in some of the meetings. Keep watching for that, and I'll be talking to you hopefully sooner than later.